So now for reference, we are using a BSL book of transport phenomena, and now we will move on to the equations for shell balance for mass transfer. So first of all, we will write the conservation statement, which is very similar for every conservation that we have written. For mass balance, conservation statement goes something like rate of mass in minus rate of mass out plus rate of production of mass A by homogeneous reaction. So this rate of production can be divided into two parts. First would be our generation. If suppose our species is A, and if it is getting generated, we will add a positive sign, and if it is getting consumed, we will add a negative sign, and which will be equal to 0, because we are taking our assumption that this is a steady state. So for steady state, we know that our accumulation is 0. Now moving on. For the first part, we have diffusion through a stagnant gas film. Okay. Now for seeing the diffusion through stagnant gas film, we will first look at the diagram. So we will assume that there is a tube like this, and the lower part of the tube is filled with a liquid A, and the upper part is species B, which is flowing as gas. So this is a thin tube. Now what we do for any conservation, we will first take a differential part. So this part, let's say this is our differential shell, and its thickness is delta Z. Now moving on, we will it is given that the surface area of this is S, so the volume of this differential shell would be S into delta Z. And there is one more assumption, that we have assumed only A diffuses, that is the diffusion is diffusion of A in non-diffusing B. This will make our calculations much easier. So we also, now moving on to the next part, we know that the rate is given as flux into area. So we will first see what is the rate of mass in. So in will be S into rate of flux in, Na at Z. We have assumed that the mass is going from this to this. So we have assumed this direction because we know that the concentration of A is maximum here, and the concentration of A is negligible here. So as we know that species move from higher concentration region to lower concentration region, hence it is moving from surface Z to Z plus delta Z. Now we know that in would be area into flux. So area is our S and flux is NaZ at position Z. Now output would be S into NaZ at position Z plus delta Z. And we have also assumed that our accumulation is 0. And since no reaction is taking place here, we will also take that the rate of production through reaction is also 0. So how do we solve questions like this? First we will write it in the form of balance equation. So it would be in at position Z minus out at Z plus delta Z is equals to 0. So how we will solve this type of differential equations? First we will divide the both sides by delta Z. So if we will divide 0 by delta Z, it will remain 0, and if this we divide by delta Z, it will be something like this. Now we will put our limit, which is delta Z is tending to 0. So this is of the form of differential equation, which is given as dNaZ by dz is equals to 0. So we obtain this equation, we will number it as 1. Alright, now moving on, we will assume we have to integrate it to get our flux. We will assume that flux through Z direction, Z is basically this direction, is constant. So we can assume NaZ is Na naught. So flux is constant through z direction. Now to get the concentration profile, what we usually need is we obtain it by applying Fick's law. So Fick's law is given for binary system as shown in the book. This is the combined flux where NaZ is the total flux, and this is the molecular flux, and this is the convective flux. Since we have non-diffusion of A through non-diffusing B, we will take NBZ this term as 0. So since NBZ is 0, we can rewrite this equation as NAZ is equals to minus C DAB dou XA upon dou Z plus XA into NAZ. So we will now rearrange and get NAZ. NAZ would be equal to, we will take this term here and then minus C DAB dou XA by dou Z remains same, and this would be 1 minus XA. So we will number this equation as 2. Now we will put our 2 equation in our first equation. So it would be something like d by dz into na. Na value we will take from equation number 2. So c into dab upon d dou xa upon dou z 1 minus xa. This is our c, which would be equal to 0. Now we know that C dab will remain constant, so we can take it out of the differential and we will multiply it here, and we know that any number multiplied or divided by 0 will remain 0. So this equation will change to, this equation will simply change to dxa dz into 1 minus xa is equals to 0. So we will solve the differential by taking the constants as C1. So it would be 1 minus xa dxa upon dz is equals to C1. Now we have got this equation and we will solve it further. So we can get the equation as ln 1 minus xa is equals to C1z plus C2 on solving this differential again. So we got now two constants, C1 and C2. To integrate it, first we would need to replace our constant C1 and C2. So we can replace C1 by minus ln K1. This is our assumption that we can replace it, so as to it will make our calculations easier. And we will replace C2 by minus ln K2. So putting it in this equation will give us 1 minus xa is equals to K1 square K2. To solve this constant of integration, which are K1 and K2, we would need boundary conditions. Now which boundary conditions will we take? So it is given in the book at the starting that the concentration at surface can be specified. For example, X is XA0 and the mass flux at the surface can also be specified, which is NaZ is Na0. So using these two boundary conditions in a diagram here, for first boundary condition would be at z is equals to z1, which is this point. Xa would be xa1, and at z is equals to z2, which is this point, xa would be xa2. So we will put these two boundary conditions in the equation and we will get the value of K1 is 1 minus xa2 upon 1 minus xa1 1 by z2 minus z1, and similarly we can get K2 as 1 minus xa1 1 minus xa2 upon 1 minus xa1 raised to the power minus z1 by z2 minus z1, so that our problem solving would be much easier. So now moving on, we got our equation as 1 minus xa is equals to K1z into K2. Now to get our constant of integral, which is K1 and K2, we would need to use boundary conditions. So how we will use the boundary conditions? We will refer the book. In the starting only it was mentioned that the concentration at a surface can be specified. For example, X is Xa naught. So we will move on to the diagram here. So here is a diagram. This, let us assume that this surface is Z1 and this is Z2. So our first boundary condition would be at Z is equals to Z1, Xa is equals to Xa1, and second boundary condition would be at Z is equals to Z2, Xa is equals to Xa2. Right. So we will now solve and get the value for K1 and K2. Now you guys must be wondering how we will get the value of K1 and K2. So we know that our Na. So we know that our Na is equals to DAB 1 minus Xa Z2 minus Z1 into dxa upon dz, which was our second equation which we got from generalized equation for fixed flux. So we will now solve to get Z. We will write the 1 minus Xa. We will bring all the Xa terms on one side and then the Z terms on other side. So we know that this is constant. It will go here and we can just assume it as constant. And then this would go as dz upon Z2 minus Z1, and we will take the limits. We know that at Z1 our Xa is 1 and at Z2 our Xa is 2. So our LHS of the equation, which is this part, will become ln 1 minus Xa at x, limit would be from Xa1 to Xa2, is equals to ln 1 minus Xa2 minus ln 1 minus Xa1 after putting the values, and our RHS would, which would be this term, would become Z minus Z1 upon Z2 minus Z1. Limit would be ranging from Z1 to Z2, would be Z2 minus Z1 upon Z2 minus Z1, which is 1. So we can write the LHS is equal, we can write LHS is equals to RHS as ln 1 minus Xa2 minus ln 1 minus Xa1 is equals to 1. So this comes out to be of the form 1 minus Xa2 upon 1 minus Xa1, and we will remove the ln from this side, so it will go as e to the power 1. So we get our K1 as 1 minus Xa2 upon 1 minus Xa1 into 1 by Z2 minus Z1, and we will get our K2 as 1 minus Xa1, 1 minus Xa2 upon 1 minus Xa1 की power minus Z1 by Z2 minus Z1. 1. Yeah, so we get the values of K1 and K2, and this would be our equation number 3. So putting this value in of K1 and K2 in equation 3, we will get 1 minus Xa upon 1 minus Xa1 is equals to 1 minus Xa2 upon 1 minus Xa1 Z minus Z1 power Z2 minus Z1. Now we know that Xa plus Xb is 1 because mass fraction of A and mass fraction of B, if there are only two species A and B, so mass fraction of A plus mass fraction of B would be 1. Similarly, we can say that X at point Z1, Xa1 plus Xb1 is equals to 1, and similarly at point Z2 we can say that Xa2 plus Xb2 is equals to 1. So we will get 1 minus Xa is equals to Xb, 1 minus Xa1 is equals to Xb1, and 1 minus Xa2 is equals to Xb2. Now we will get the flux of A. To get the flux of A, we will now move on to our equation number 2, which was this. So we will rewrite the equation by taking 1 minus Xa term inside with dxa and dz. It would be like minus C dAB 1 upon 1 minus xa dxa upon dz. So we will assume this the term which is inside the bracket, which is 1 by xa dxa upon dz, to be some constant c, because we need it to solve our differential value and get the flux curve. So for that we will take c1 is equals to minus ln k1, which we have already assumed in our previous assumption, and we also know the value of k1, which is 1 minus xa2 upon 1 minus xa1, 1 by z2 minus z1. So now we will substitute this value and we will get our NAZ. This is basically our NAZ in z direction. C DAB z2 minus z1 ln 1 minus xa2 upon 1 minus xa1. We have simply substituted the value of c1, which was minus ln k, here. So we got this equation. So we got the equation for the concentration profile of A. Similarly, to get the concentration profile of B, we can just substitute xp is equals to 1 minus xa and get it. So we will, once the concentration profiles are known, we can get average values and mass fluxes at surfaces. For example, the average concentration of B in the region between Z1 and Z2 can be given as xp average upon xp1 integration of xp upon xp1 into dz upon dz. So as we know, z is ranging from z1 to z2 and here also z1 to z2. So we will get it as 0 to 1 xp2 upon xp1 power eta into d eta upon integration 0 to 1 d eta. So we will get it as xp2 upon xp1 eta ln xp2 upon xp1 ranging from 0 to 1. So you must be wondering what is eta that we have taken here suddenly. Eta is nothing, it's just basically eta is z upon z1, z2 minus z1, basically the equation of slope. It is a dimensionless variable, dimensionless length variable. We use dimensionless numbers in our equation so that our calculations can be simplified. So we will get xp average is xp2 minus xp1 upon ln xp2 upon xp1. So this is the average value, and also we know that the average value of xp is the logarithmic mean. We know that for a logarithmic mean we write it as a2 minus a1 upon ln a2 by a1, and this equation is of this form. So this is the xp average is equals to xp log mean. Since now we have seen all the equations, let us see the diagram which is given in the book. At z is equals to z1, this is our xa value and here we have z value. So xa is ranging from 0 to 1 and z is ranging from z1 to z2, which is basically z1 is here and z2 is here. So we know that when xa1 would tend to 1, xp2 would be 0. So here xa1 is tending to 0, hence xp1 is tending to 1. And similarly at z2, because here only liquid A is present, so higher concentration of A is present, whereas here there is lower concentration of A and higher concentration of B. So since xp2 is tending to 1, xa2 is tending to 0. So now our first topic is finished. We will now move on to our topic number 2, which is basically diffusion with a homogeneous chemical reaction. And the reaction that we are assuming is A plus B gives AB. And we have also assumed that it is 3 to 1. So this is basically our first order irreversible reaction. And we have taken the rate would be minus RA triple dash is K1 triple dash into Ca. Since we know that rate is equals to flux into area, we will write the mass balance equation here, which is momentum in at position Z is equals to Z, and momentum out at Z is equal to Z plus delta Z would be equal to 0, because plus, but what we will have here is reaction. So we will add, so in minus out plus formed by reaction. So it would be like NAZ at Z into surface area, which is S, minus NAZ at position Z plus delta Z into surface area, which is again S, minus K1 triple dash Ca into S into delta Z. Here S into delta Z is basically the volume, because here we are getting mole per meter cube second, but we need a mole per second. So we will multiply by volume, and the unit of volume would be meter cube. So this meter cube and this meter cube would get cancelled, and we will just be remaining with mole per second. So this equation again we will divide it by delta Z, and then take the limit as delta Z tending to 0. So we will get a dNAZ upon dz plus K1 triple dash Ca is 0. Since this was minus and this we will get as minus dNAZ by dz, we are taking it on the right hand side, and left hand side will become 0, so this will become positive. Now moving on, if the concentration of A is small, let's suppose it's tending to 0, then we can take our assumption as NAZ is minus DAB dCA by dz. Since the total molar concentration C is virtually uniform throughout the liquid, we will combine this equation with this equation. Let's first number these equations. This would we will take as suppose 1, and this we will number as 2. So combining 1 and 2, we get DAB d square Ca upon dz square minus K1 triple dash Ca is equals to 0. Now we will need to solve this equation again by boundary conditions. So what would be our boundary conditions? It would be same as a previous one. Here from the book we will see, instead of the second part B, the mass flux at a surface can be specified. For example, NAZ is equals to NA0. So for the first boundary condition, we will write at Z is equals to 0, Ca is equals to Ca0, and at Z is equals to L, NAZ is equals to 0, or basically NAZ is dCA by dz. So dCA by dz is equals to 0. Now we are going to multiply this equation. Since this is dz square, basically it is L square, we need to remove this term. Hence we will multiply the equation number 3 by L square Ca0 dAB, because we need to write it in dimensionless form, and this z square and this L square would get cancelled, and in the dimensionless form our equation would be something like d square upon d eta square minus phi square t is equals to 0. We need to make it of, this is basically a second order differential equation. So to get the solution for second order differential equation, we need to make it of the form d square y by dx square minus a square y is equals to 0. This is our second order differential equation. So for the solution of this, we already know from mathematics that the solution to this equation would be c1 cos hyperbolic ax plus c2 sine hyperbolic ax. So we are taking this eta. What is eta? Eta would be our z by L to make it in dimensionless form. Similarly, our this would be Ca upon Ca naught, and phi would be K1 triple dash L square upon DAB. This is all the constant terms. So our equation would become something like C1 cos h phi into eta plus C2 sin h. Since our A is phi, from this comparing this equation and this equation, our A is phi. So into phi epsilon. So to solve this equation, we will again need boundary conditions. Now what would be the boundary conditions here? Our first boundary condition would be at z is equals to 0, eta is 0. Now you must be wondering how eta would be 0. Since eta is equals to z by L and z is 0, hence our eta becomes 0, and this term is Ca upon Ca naught. So it basically becomes 1 because at z is 0, our C is Ca naught. And second boundary condition would be at z is equals to L, eta is equals to 1, and this term is 0. Since z by L is eta, so L by L is 1, and this is because our Ca at z is equals to L is 0. Hence we get two boundary conditions. So when the constants of integration are evaluated, we get our value for this and eta. Now reverting to the original equation, we get phi m. So we get the equation for gamma and eta. So the equation for gamma is cos h phi 1 minus eta upon cos h phi. So reverting to the original notation, we can write Ca upon Ca naught, because our gamma was C upon Ca naught, is equals to cos h, and by placing the value of phi, which we have assumed phi square equal to k1 L square upon DAB, so phi would be k1 triple dash L square by DAB, but under root, and upon cos h k1 triple dash L square by DAB into 1 minus z by L. So this is the hence we obtained our concentration profile. Now once we have the complete concentration profile, we may evaluate other quantities such as the average concentration in the liquid phase. So average concentration would be given as Ca average upon Ca naught, again like we did previously, Ca naught to get the average fraction. Similarly, we are repeating it. Since we know that our z is varying from 0 to L, we are placing the limits. This is of the form tan h phi upon phi. Also, the molar flux at the plane z is 0 can be found by NaZ at z is 0 minus DAB dCA by dz at z is equals to 0, and we know that at z is equals to 0 it can be rewritten as Ca naught DAB upon L into phi into tan h phi. Hence we obtain this and this value. We obtained concentration profile, then the average value, and now the flux at z is equals to 0. So now to summarize everything, we will look at the diagram. We see that this is a thin tube, and here it is delta z, our differential element. So flux is entering from here and leaving from here, and we know that at z is equals to 0, Ca is Ca naught, and z is equals to L, Ca is Ca. So we will plot this type of equation.